All right, let's work another pathways problem. This is 2.48 from your textbook. This is another interesting problem. You'll probably see stuff like this in the homework and potentially on quizzes and exams and things like that, okay? So it's an interesting little problem. It's also interesting from a perspective of understanding where the numbers for atomic masses on the periodic table of the element actually come from. Because any sample of an element that we're going to interact with and use in experiments is a distribution of naturally occurring isotopes, that number for atomic mass in the box actually really corresponds to no particular isotope generally. Instead, it's actually a weighted average of the naturally occurring isotopes. And this problem is really going to demonstrate that nicely, okay? So what we're asked to do here is compute the atomic mass of magnesium in atomic mass units, or AMU, given the information that the magnesium has 3 naturally occurring isotopes that are common in the following abundances. Okay, so we have magnesium 24, magnesium 25, and magnesium 26. And we're told in the problem magnesium 24 is by far the most abundant. Just under 79% of this or just under 79% of all magnesium is this isotope. Magnesium 25 is about 10%, magnesium 26 is a little over 11. And each of these different isotopes, of course, have their own mass associated with that isotope. And note that these are different, right? And that makes sense because we know that each of these has differing number of protons. As we go from 24, 25 to 26, we're picking up an extra proton. Protons have significant mass, so the isotope mass also goes up. So how can we use the information on abundance and isotope mass to compute what we should report as the isotopically abundantly averaged atomic mass? And again, this is the average that's representative of all magnesium that we're going to interact with in our experiments in nature here on Earth, okay? So how will we do this? Well, it's pretty simple mathematically. Basically what you do is you're going to add together a series of terms. The first term will be for isotope number 1. Here that's magnesium 24. And then we're going to have a second term and a third term for magnesium 25 and 26 in a second. But basically what we need to do is take what's called the fractional abundance and multiply that by the mass of that particular isotope. So the mass of magnesium 24 is this number, 23.9850. So we'll take that mass and we'll multiply it by a fraction. And this fraction, I like to call that the fractional abundance of that isotope. And what I mean by that is it's not a percent abundance, but rather it's a fractional abundance. In other words, if you sum all the abundances, you get 1. In percent abundance, you sum all the abundances, you get 100. That's what's characteristic of a percent rather than a fractional amount, okay? So to compute the fractional abundance, I'm going to take the percent abundance, 78.99, and just divide by 100. So it's like moving the decimal places, 2 spots to the left, basically. So what you end up doing then is you multiply that fractional abundance times that isotope mass, and that gives you a contribution for that particular isotope. And you just do this over and over. So the next term will be for magnesium 25. And then I'll have a third term for magnesium 26 here in a second. Now, magnesium 25 has a much smaller fractional abundance. It's 10 over 100. And then I need to multiply that by its mass, 24.9858 AMU. That's my contribution for magnesium 25. And similarly, over here on the far side of the board, I'll have my term for magnesium 26. That's going to involve taking 11.01, dividing that by 100, get my fractional abundance, and then multiplying it by its isotope mass, which is 25.9826. I ran out of space here, so I'm not going to be able to write that, unfortunately. But you keep those digits of precision. Okay? See that? All right, now, if you go ahead and you do this, well, I guess I'll just write it down here, okay? You get numbers for each of these results, okay? So for instance, here, if I'm looking at my computer screen to get me the number that I computed for this first one, if you do the math on that, the 78.99 divided by 100 times this 23.98, you end up getting 18.9457. Okay. And you get a result for magnesium 25's contribution to the total, which is 2.49858. And then you add that to the last one, which is 2.86. That was the heaviest and a little bit more abundant than this one, so it makes sense this number is a little bit bigger than this one. So you get these mathematical terms for magnesium 24, 25, and 26, and each of these then correspond to sort of the total from that particular isotope, if you want to think about that way on a weighted average. So all we're really left to do here is to add these three numbers up, just sum them together or add them up. Okay, and if you do that, you end up getting 24.305, right about that, AMU, for the weighted atomic mass of magnesium across all three of its naturally occurring isotopes. Right? So that's more or less how you do this problem. Now, interestingly, if you look at the number that's on the periodic table for magnesium in its box, just in your book, you'll see 24.31. What we just computed is the number that's in the box on the periodic table. Not just for magnesium, but the other elements as well are computed the same way. The number that's in that box is a weighted average that's based upon the abundances of all the naturally occurring isotopes of atoms of that particular element. Okay, so while the story will be different, for tin or sodium because they have different isotopes, different abundances, that number is always computed in the same way. You just make a tabular data of the percent abundances of every isotope and the masses of each isotope, and that's where that number comes from. Okay, so just to kind of give you some advice, or I don't know if you want to keep it a word of warning or whatever. You really want to know how to do this computation and where these numbers come from. Because here, we kind of worked the forward problem, where we were trying to find the atomic mass. You might see in the homework or online quizzes or even an exam where you have to work the reverse problem. Now what I mean by that is I could have given you the atomic mass, and maybe I even would give you 2 of the 3 of the percent abundances, what these isotope masses, and ask you to find the third percent abundance, or maybe find the isotope mass of one of them. So we could work the reverse problem, and it just becomes an algebra problem. Okay, if you know the equation and how this number is computed, it just becomes an algebra problem where you'd have an x somewhere, an unknown variable, and you could rearrange the equation and solve. That's also a common type of problem to see.